Hey guys, today we're going to look at forces on an inclined plane. So the first thing we have to look at is an object on an inclined plane, and we have to remember some of the forces that we've talked about in previous units, including force due to gravity and normal force and how their vectors look. So on this inclined plane, your force due to gravity has to be drawn directly towards the center of the Earth. So this is our FG arrow. And our normal force has to be drawn perpendicular to the surface. So this is our Fn. The issue with objects on an inclined plane is that we are no longer in a normal XY coordinate system. We have to either shift our perspective or shift the drawing in order to be in a coordinate system that we can use. So as of right now, we have the Fn going up and at an angle and Fg going downwards. I can either split Fn up or I can split Fg up. I'm actually going to choose to split Fg into two vectors, and here's why. Due to some math laws, there's an interior angle theorem that says that this angle of the incline is equal to this angle inside these two vectors. Because of that means I want to split up the FG and not the FN, because I know these two angles have to be equal. So I want to solve for the green line and I want to solve for the blue line. Here's the issue. I'm going to go ahead and remind us of SOHCAHTOA over here. Using SOHCAHTOA, sine solves for the opposite leg, cosine solves for the adjacent leg. So now, since we are on an incline, those numbers are actually slightly different. So I'm going to add symbols to my diagram. This is FG in the x direction, and this is going to be FG in the y direction. And using this inside angle, FGX is now my opposite leg. So I'm going to use FGX equals FG sine theta to solve for the x component of the gravity. And I'm going to use FGY equals FG cosine theta to solve for the y component of the gravity. So the issue with this is everything in the x direction in the past we've used cosine. Now that it's on an inclined plane, we do have to flip-flop our thinking. Think about the vectors in terms of opposite and adjacent, and you see that we need to use sine for the x direction and cosine for the y direction, even though it's different from the examples we've done in the past. So we can use interchangeable terms to describe these components. If a force is perpendicular, it is perpendicular to the surface, which is what we consider the y direction. This direction is almost always an F net of 0, which means FGY is always equal to Fn. These 2 points are really, really important. If a force is called parallel, that means it's parallel to the surface, which is what we consider the x direction. This direction almost always uses the F net equation that has a value or that allows acceleration to take place. So keep in mind, perpendicular is y, parallel is x. So on this diagram, I'm going to set up my F net equations. These are the basic equations that we're going to be using from now towards the end of this unit. So we have FG going directly downwards. We have Fn going up at an angle. We have FGY. And we have FGX. So right now, F net in the x direction, the only vector we have is FGX. If we use friction, we would have F net in the x direction is FF minus FGX. And in the y direction, F net y equals Fn minus FGY, but F net y is going to be 0. which leaves us with FGY equals Fn. So we have this equation, F net x is FGX, given the photo up top. F net x is F minus FGX if we include friction, and FGY equals Fn. These are all equations that we're going to be able to use. So, first example problem. A crate weighing 45 kilograms is resting on an inclined plane at 30 degrees above the horizontal. Find the components of the weight forces that are parallel and perpendicular to the plane. So first thing I'm going to do is draw FG going down, break it apart into my two vectors, and it's asking me to solve for FGX and FGY. So on a previous slide, I gave you the equations that you're going to use to do that. FGX equals FG sine theta, because this blue line is the opposite leg. FGY is FG cosine theta, because this green leg is the adjacent leg. And remember I said that this angle is equal to this angle. So the one thing that they haven't told us is FG. FG is actually mg, just like it has been in previous units. So FGX equals m times g times sine theta. FGX equals 45 times 9.8 times sine 30. FGX equals 225.4 newtons. I'm going to do the same thing with FGY. FGY equals m times g times cosine theta. And FGY equals 381.91 newtons. So blue arrow, green arrow, those are my two values. So the next step of this problem, there are 200 newtons of friction acting on the crate. Calculate the acceleration of the crate down the ramp. So on the previous slide, we said that F net in the x direction is FF, because that's the positive direction, minus FGX. Now, any F net ever can be substituted with an m times an a. I'm going to put a little x next to that a to remind me it's the acceleration in the x direction. FF is 200 newtons, and FGX was calculated out to be a value of 225.4 newtons. So 45 times a in the x direction is negative 25.4 newtons. Divide out by 45 on both sides, and the acceleration in the x direction is negative 0.56 meters per second squared. Now that negative simply means that this box is traveling in this direction down the ramp. One more practice problem. There's a couple questions to this problem, but we're going to work through them as we go. So a ramp is at an angle of 25 degrees with the horizontal. A 10 kilogram box is held in place on the ramp. What is the FGY of the box? So FGY is FG cosine theta. FG is mg cosine theta. So 10 times 9.8 times cosine 25. And FGY is 88.8 newtons. What is the FGX of the box? Same thing, only using sine instead of cosine. and Fgx equals 41.4 newtons. If we remove the force holding the box in place and ignore friction, what is the net force acting on the box? So F net in the x direction is equal to Fgx, which is actually a negative value since it will be sliding down the ramp. So F net in the x direction is negative 41.4 newtons because of the direction of the sliding. What will the box acceleration be when it's released? So F net in the x direction equals negative 41.4 newtons. Substitute m times a in the x direction equals negative 41.4 newtons. The mass of the box is 10. So that means the acceleration in the x direction is negative 4.14 meters per second squared. So that box accelerates down the ramp at 4.14 meters per second squared. And it's negative again because of the direction going down the ramp. So when you get into class tomorrow, what we're going to be doing is looking at free body diagrams in 2 dimensions, as well as calculating unknowns in 2 dimensions. So I'll see you tomorrow.